Good morning, students. Today we are going to discuss a very important topic of your module 4, that is in bound quantum state. The topic is rigid rotator. In this rigid rotator, we assume the two masses. Okay, the two masses which is attached with each other by an attractive force. Okay, we assume there is an interatomic forces between these two masses, and it will rotating about an axis. It will rotating about an axis. Okay, and meanwhile in rotation it will passing through the center of mass. Okay, we assume that the origin O, that is in center of mass, the rotation of this mass will be passing through a center of mass. Okay, so in this case, when the plane of revolution is fixed, it is called a rigid rotator with fixed axis. Okay, so we have to find out the wave function. Okay, wave function is not so important for your end semester examination, but we have to find out the energy eigenvalue of a rigid rotator in fixed axis. Okay, so in order to find out the energy eigenvalue of rigid rotator, we have to first assume the two masses that we already discussed. The mass one, that is mass one, that is attached to a body. Okay, simply we assume that there is a two body is mounted by the rotating reference frame. Okay, the first body which has a mass and which has a position coordinate will be written like this, and the second body which has some mass and which has a position coordinate will be written like this. Okay, and the center of mass which has to be assumed to be 0, because by the reference frame, by the plane reference frame of this body having mass m1 and m2, the center of mass will be this is assumed to be 0. Okay, so the moment of inertia, in order to find out the energy eigenvalue, we have to first define the moment of inertia of the different body which is associated with some mass. Okay, the moment of inertia of the whole system will be written like this. Okay, this is the simple moment of inertia term, because the moment of inertia of a mass will be defined as mr square, but we are defined as a 2 mass here. Okay, so the complete moment of inertia of the whole system will be written like this. Okay, so we will define as a x coordinate, because we cannot define in a 3-dimensional way, so we will take an as a x coordinate for the simplification of this rigid rotator problem. We have to define as a x coordinate, and for the x coordinate the center of mass will be defined as this. Okay, if we taken as the center of mass as a origin, we define at the center of mass at x coordinate will be this equation. This is quite simple, and we assume that the center of mass is already assumed to be 0, that we have already discussed that this term has to be 0. So in this case we have to define the center of mass is 0, and in this case further simplifying the equation, what will get mr1 equals to mr2. Okay, so we have assumed this is the distance of mass 1, that is the body 1 at a distance from origin. This is the distance from origin of body 2, and the total distance will be taken as r. Okay, so in order to replace r equals to r1 plus r2, what will get? If you put r equals to r1 plus r2, the equation for the simplification of this equation, we will get r2 equals to m1r divided by m1 plus m2, and further r1 will be defined as m2r divided by m1 plus m2. This is the simple mathematical calculation we have when we have to put the r equals to r1 plus r2. This is the result. Okay, then now on putting the value of r1 and r2 in the moment of inertia equation, that is I equals to m1 r1 square plus m2 r2 square, when we put the r1 r2 value in equation 1, that is the moment of inertia equation, this will get this kind of equation. Okay, so we have assumed this kind of constant m1 into m2 divided by m1 plus m2, we have denoted as mu. Okay, so this is for the two body system in which we consider there is a mass 1 and the mass 2. Okay, and the next step what we'll do, we will have to be replace the two body system into one body system with a reduced mass. Okay, so what will happen if we have to be reduced, if we have to be replace the two body system with a single body of reduced mass, and it has to be placed at a distance equal to the separation between the two mass. Okay, so this mu term will be represent as, because it's a constant, we will define as here, and this has to be defined as 1 divided by m1 plus 1 divided by 2, because these reference these has to be replaced with a single body. Okay, the two body has to be replaced by the single body, and this term has to be denoted as the single body system with a reduced mass. Okay, so this single body with a reduced mass is defined as this kind of equation. Okay, so next, as the two body has reduced mass to a single body, its total energy will be taken as a kinetic energy. So in this case, the potential energy is taken as a 0. Okay, so the whole energy will be defined as the kinetic energy, and for the kinetic energy we know that this is half mv square. Okay, m is taken as a reduced mass here, because 1 by u or mu is taken as a reduced mass. Okay, so the kinetic energy represent as 1 by 2 u x dot square y dot square plus z dot square. Okay, this is the definition of kinetic energy, because in this case because we have to replace the two body system into one body system, so in this case the potential energy is 0, because the revaluation the rotation is also happening, and for the rotation of axis the potential energy tends to 0, so we will only left the kinetic energy term. Okay, so in order to define the eigenvalue energy eigenvalue of rigid rotator, we have to define the Schrodinger wave equation in spherical polar coordinate. Okay, so in this case the distance vector or the first term of the Laplacian operator of Schrodinger equation will have to be 0. Okay, let's see. So the kinetic energy of the body which has a reduced mass, which can be represented as this in spherical polar coordinate. Okay, this is the one of the expansion of representing the kinetic energy in spherical polar coordinate. So this equation must have to be remembered. Okay, so in this case the radius of circular path is constant. Okay, we already know that the radius of circular path is always constant, because it is a rotatory motion and the body is continuity rotating in a single reference frame. So in this case the circular path, the radius of circular path is always 0. So in this case the first term will be 0, and so what the left terms are here. Okay, so we know that when we put into the Schrodinger wave equation as a Laplacian operator, what will we get? This is a time dependent Schrodinger wave equation, we have already known. And for the rigid rotator case, in this case the time dependent Schrodinger equation can be written like this, because the v is 0, we have already discussed, because this is the rotating reference frame. In this case the potential energy is always 0, so we left the total energy term. Okay, so in this case the E term, so E term will be taken as for granted, and in this case the V is 0, so we only left with 2 mu E. Okay, we have to assume here a single body, and the single body which is associated with the reduced mass, so we have to replace as m for mu. Okay, we have to replace mu in m, so the equation will be written like this. Okay, so we know that for the Laplacian operator, or we can define the Schrodinger wave equation in spherical polar coordinate. The spherical polar coordinate, the Schrodinger wave equation will be written like this. Okay, this is the expression of Schrodinger wave equation in spherical polar coordinate, and this equation has to be remembered. Okay, because this is the only way to further solve the problem in spherical polar coordinate in order to find the energy eigen value of rigid rotator. Okay, so we already know that the radius of circular path is always same, so we can take as a first term as a 0, or we can say the distance of a particle from the axis of rotation is constant, that we have already discussed. Hence the first term of the above differential equation is always 0. Similar this kind of case, when the radius of circular path is constant, so the first term is 0. So in this case the first term of differential equation is always 0. Okay, so this kind of equation can be solved by the separation of variable. We have already discussed in the particle in a three-dimensional box. We have to solve this kind of spherical polar coordinate form in the separation of variable terms. Okay, so this kind of similarly this kind of equation can be drawn, that is the psi is a term, because there is a two term, that is theta dependent as well as the phi dependent, the theta dependent as well as the phi dependent. So this theta dependent and phi dependent can be reduced by the capital theta or the capital phi. Okay, so according to the separation of variable phenomena, this can be expand like this. Okay, and this has to be replaced in the above equation. Now we have further simplified this equation, the phi term and the theta term, and this has been already expanded in the three-dimensional problem, particle in a box in a three-dimensional. And when we substitute this the capital theta and the capital phi term in above equation, we will get this kind of equation, and we further multiply and divide with capital phi and capital theta, and further multiplication with r square. Okay, हम लोग ऊपर नीचे न्यूमरेटर डिनोमिनेटर में कैपिटल थीटा और कैपिटल फाई को डिवाइड और मल्टीप्लाई करेंगे, और उसमें फर्दर आर स्क्वायर पे मल्टीप्लाई करेंगे. ओके, तो ऐसा करने पे हम लोगों को ये टर्म मिलेगा. और यहाँ पे क्या है कि जब हम लोग आर स्क्वायर से इसको मल्टीप्लाई करेंगे तो यहाँ पे म्यू आर स्क्वायर. ओके, म्यू को हम लोगों ने लाइक रिलेटिव मास और इफेक्टिव मास से डिनोट किया है, एंड दिस इफेक्टिव मास हैज बी टर्न आउट विद द मोमेंट ऑफ इनर्शिया. सो मोमेंट ऑफ इनर्शिया वी नो that it is written like mr square. So the moment of inertia in terms of effective mass will be written like mu r square. Okay, it is denoted as I. Okay, further multiplication of sine square on solving this kind of equation will get like this. Okay, so हम लोग उसको थीटा टर्म और फाई टर्म में सेपरेट करेंगे, बिकॉज उसको फर्दर उसको सॉल्यूशन निकालने के लिए हम लोगों को इसको थीटा टर्म और फाई टर्म में सेपरेट करना पड़ेगा. ओके, सो यहाँ पे साइन थीटा टर्म है, यहाँ पे साइन थीटा टर्म है. सो ये दोनों को हम लोग इसको एलएचएस में कंसिडर करेंगे और इसको हम लोग आरएचएस साइड ले जाएंगे. सो इस तरह हम लोगों ने इसको यहाँ पे ले गया, एंड फर्दर this solution is completely dependent on phi, and this the RHS side is completely dependent of capital phi. Okay, this term is dependent upon theta, this is capital theta, and this term is also dependent upon the capital phi. So हम लोग इसका solution निकालने के लिए इसको हम लोग m consider करेंगे. So we have to first consider this equation as a m. So this differential equation can be simplified. This equation can be further simplified in this kind of term, and the solution of differential equation, because ऐसा सॉल्यूशन, ऐसा डिफरेंशियल इक्वेशन को हम लोगों ने कई बार इसका सॉल्यूशन निकाला है, एंड पहले भी हम लोगों ने इन द थ्री डायमेंशनल प्रॉब्लम और पोटेंशियल इन इनफाइनाइट स्क्वायर वेल में भी हम लोगों ने इसका सॉल्यूशन निकाला है, एंड दैट हैज टू बी सॉल्यूशन लाइक दिस. ओके, एंड फर्दर जो हमारा जो कैपिटल थीटा पार्ट है उसको हम लोगों ने इस तरह से डिनोट किया, बिकॉज हम लोगों ने जो टर्म है, जो फाई टर्म, कैपिटल फाई टर्म है, उसको हम लोगों ने एम स्क्वायर से डिनोट किया था, जस्ट लाइक दिस। ओके, ये बस हम लोगों ने इसका सॉल्यूशन निकाल के रख दिया है, बस हम लोगों ने इसको एम स्क्वायर के रूप में कंसिडर किया था। ओके, so after the considering in order to solve the above equation we have to assume cos theta को हम लोगों ने x माना, suppose in order to solve the above equation and we know that जब इसको डिफरेंशिएट करेंगे del x by del theta, जब इसको हम x को डिफरेंशिएट करेंगे तो it will give the differentiation of the cos x equals to minus sin theta। okay, जब cos theta को हम लोग डिफरेंशिएट करेंगे we will get sin theta। okay, this is simple and this has to be put in the above equation। okay, so on putting the value of x and del x by del theta, we have to further divide the numerator and denominator with the del x। okay, so for the solving the above terms, sin theta divided by capital theta, there is a del by del theta will be replaced by multiplying delta x in delta x, not it is del x, multiplying the del x on numerator side and denominator side। okay, simply this will cut, this will this is for the simplification process we have to multiply del x on the numerator and denominator side। okay, similarly in the bracket we have to be multiplied del x and del x with the numerator and denominator, and what we'll get। okay, so we know that del x by del theta equals to minus sin theta, and on multiplying the sin theta we will get a sin square theta, and in the similar way del x by del theta is sin theta, so the negative sign and this negative sign will cancel each out and we will only left sin square theta as well as sin square theta। okay, and on we have to take a common, here is a sin theta, a sin square theta, and that has to be taken in a denominator side on the RHS। okay, so the sin square theta will be written like 1 minus cos square theta, and 1 minus cos square theta in which the cos is written like x, so it will further represent like 1 minus x square। okay, so further differentiate in the u into v form, there is a differentiation will be solved like this, and we will get, because this theta term, because capital theta term is there, and this theta term in which the capital theta is common, so we will put as a common and will taken as a this। okay, so this equation is completely associated with the legendary differential equation, in which m will takes a zero value when we put the m, because here we taken as a rest mass will be zero, we will talk about the effective mass। okay, so in this case the effective mass is taken into account, in this case the m is 0, so n is 0, what will let 2ie divided by h cut square। okay, so we will replace the 2ie, that is h cut 2ie divided by h cut square with l into l plus 1, so the differential equation of legendary differential equation will be written like this। okay, so this is the differential equation, that is a legendary differential equation, and in order to find out the Schrodinger the wave function of rigid rotator, we have to solve the differential equation। okay, so in जैसा कि मैंने तुम लोगों को जो नोट्स दिया है उसमें उसका सॉल्यूशन है, वो लेजेंडरी डिफरेंशियल इक्वेशन का सॉल्यूशन है, और उसे हम लोगों ने शाई का टर्म निकाला है और उसे हम लोगों ने उसका वेव फंक्शन फाइंड आउट किया है। सो फॉर द एग्जामिनेशन दिस इज क्वाइट tedious process, and I don't think so this is not so important for examination purpose, but the only thing is you have to find out the energy eigenvalue of rigid rotator, because for the examination purpose the energy eigenvalue is very important. In your previous year questions I have seen that there is a question which is the energy eigenvalue has come into account, and this is for the examination purpose only. Only the energy eigenvalue has been taken as very important term. So this is quite complicated, and I think this might not be come in the examination, but in the notes which I have provided, that it is the solution of this differential equation has already given. Okay, and but the important thing is we have to find the energy eigenvalue of rigid rotator. So this is the term from which we have to find out the energy eigenvalue of rigid rotator. So in this case, En equals to L into L plus 1 h cut square divided by 2y. Okay, so this is the energy eigenvalue of rigid rotator which we have derived here. Okay, so what are the graph regarding it? So this is the energy eigenvalue of rigid rotator which we have discussed, and this is the energy level diagram in which when we put the different, we have to put the different value of L here, and we will get the different value of energy here. So this is the energy level diagram of the rigid rotator. Okay, this is the, for the examination purpose, this is very important, and the energy wave function which have already discussed, and the notes will already provided as in Google Scholar, so you must follow. Okay, so till then, this is the 4th video lecture till I am provided. Hope you will get this, and stay home, stay safe. Thank you.